Hi guys, can you guys hear me?
Yes.
Okay.
We can hear you, Dr. Lee.
Okay. Okay. Right. All right, I am going to continue chapter 17 and then um later today, sometime later today, when more people join the meeting, I will talk about the exam 2 that we just finished on Tuesday. Okay. So, chapter 17 is additional aspects of aqueous equilibria. Okay. Um, Before exam 2, we stopped at um, weak acid and strong acid titration. Now we will move on to something called solubility equilibria. Okay. So most ionic compounds that are considered insoluble, in fact, will still dissolve in aqueous solution to a small extent. Okay, and before exam 2, I received few emails from students, and I think you guys are still confused about this aqueous system. Aqueous system means chemical compounds dissolve in water. Okay, so most ionic compounds that are considered to be insoluble will still dissolve in water to a very, very small extent. Okay, these mostly insoluble compounds are considered to be strong electrolytes because whatever the portion of the compound that dissolves into water also dissociates. So as an example, let's say you have silver chloride. This salt is insoluble in water, okay? But although it's insoluble, very tiny small amount of silver chloride will dissociate in water, okay? It will dissociate into silver ions and chloride ions. Okay, so upon being this solid added to water, very small amount will still dissociate. Okay. Table 4.1 from chapter 4 lists ionic compounds that are soluble and insoluble. I hope you can recall this from Gen Chem 1. Okay, this table lists ionic compounds that are soluble in water, that are insoluble in water. Okay, so all the ionic compounds with nitrate is going to be soluble in water. Acetic acetate, any ionic compounds with acetate will be soluble in water, and so on and so forth. And here are the exceptions. So anything that falls into this exception, they will be insoluble. Okay. Any compounds with these anions, any ionic compounds with these anions is going to be insoluble in water. Okay. And here are the exceptions. So anything that any ionic compounds that falls into this exception, they will be soluble in water. Okay. So for silver chloride that I mentioned before here, if you look over here, anything contains chloride should be soluble. However, silver chloride falls into this exception. Compounds of silver, okay, silver cation is going to be insoluble. Okay, so according to this table, silver chloride is insoluble. However, now that's what we learned in chapter 4, but now in chapter 17, we know that although it says it's insoluble, very tiny amount will still be soluble in water and they will dissociate in water. So let's take a look at another example. Barium sulfate. Okay. So according to this table, barium sulfate, anything with sulfate is soluble. However, if it has barium, it's going to be insoluble. It falls into exception. So barium sulfate is considered insoluble in water. Okay. However, a very tiny amount will still dissociate in water. And the dissociated portion will look something like this. The dissociated portions of ionic forms, and the process is written as an equilibrium because dissociation only occurs only to a small extent. Okay, so for here, I should use the arrow pointing both sides. Okay. So therefore, the equilibrium constant expression can be written for this process, which is labeled KSP. KSP exists. The KSP is the equilibrium constant for the equilibrium between ionic compound and saturated solution. The magnitude of this KSP shows the degree of which the compound can dissociate in water. Okay, it measures how much of the solid dissolves in water to form a saturated solution. The smaller Kp indicates smaller amount of solid being dissolved or being dissociated in aqueous solution. Higher KSP value indicates quite larger amount of solid that can be dissolved or dissociated in aqueous solution. So how do I write the equilibrium constant expression for these slightly soluble ionic compounds? Since we do not include solid in the equilibrium constant expression because they do not vary in concentration, right? So we will exclude barium sulfate salt in the denominator, okay? The equation for KSP is going to be product concentration divided by reactant concentration, right? H raised to a power equivalent to a coefficient. But as for the reactant, we have barium sulfate, which is solid, so we're not going to include barium sulfate solid in the reactant. So there's nothing in the denominator, okay? So KSP is just a product of concentration of barium ion and sulfate ion, each raised to the power equivalent to their coefficient, okay? The coefficients are 1, so it's raised, but they're both raised to the power of 1. Here's another example, okay? Barium phosphate is going to very tiny little portion will dissociate in water, generate barium and phosphate. Okay, the KSP is going to be concentration of barium raised to power of 3, coefficient 3, phosphate raised to power of 2 because it has coefficient of 2. Let's try a sample exercise. Write the expression for the solubility product constant for calcium fluoride and look up the corresponding KSP value in Appendix D. Okay, so behind the textbook, Appendix D, there are lists of KSP values for these insoluble ionic compounds, or more correctly, slightly soluble ionic compounds. Okay, the KSP value for calcium fluoride from Appendix D is found to be 3.9 times 10 to the negative 11. Okay, so now we need to write the expression, equilibrium reaction and equilibrium constant expression. So if tiny bit of this salt dissociates, dissolve in water, dissociate, it will generate calcium ion and fluoride ion. Okay, the expression for KSP is going to be calcium raised to power 1 concentration of fluoride raised to power of 2. Okay, we're not going to include calcium fluoride solid in the denominator, okay, because it's solid. So yeah, that's it. That's the expression for the solubility product constant for K calcium fluoride. All right, let's see how many people have joined the meeting. We have about 38 students. Okay, so I need to talk a little bit about the exam 2 that you guys finished on Tuesday. It looks like a lot of you guys were experiencing difficulties with chapter 16 and chapter 17, and that's totally understandable. Those are very, very challenging chapters. Okay, so I am not going to put this in the announcement section. Okay, so this if you guys are here today, you guys are very, very lucky. What I am going to do is I'm going to allow you guys to make exam corrections. Okay, so anybody who joined today's meeting, if you guys are, if you guys desperately need to boost your exam 2 grade, I mean, if you're satisfied with your current exam grade, that's totally fine. Okay, you don't have to do exam corrections. Okay, this is not a requirement. You're not obligated to do the exam correction. But if you really, really, really want to boost your exam grade, what I can do for you is I will send me an email. Okay, talk to me about your situation. I will hand you over the exam. You can resolve the questions that you missed on the exam. So if you log on to Web Campus, you're going to be able to see what questions you missed. Okay, so you will use your handwriting, resolve the questions that you missed on the exam. For each question you got incorrect on the exam, you need to write out detailed solutions. Put the correct answer in a box, and if you resolve that incorrect question correctly, I will give half of the points back to you. Okay, so let's say, for example, you got 70 points for the exam. That means you lost 30 points. If you do exam corrections, if you get all of those questions correctly, the maximum points that you can get back is 15 points. Okay, but note that exam correction will be graded, so this is a max point that you can earn, but it doesn't guarantee that you're going to get full 15 points back. Okay, so if you do the exam correction, if you're at 70 points, it can boost your grade up to 85 points. So if you are in a desperate situation where you really, really want to improve your exam score, or if you really want to or even if you don't want to do exam corrections, if you want to have the exam in your hand, I will hand you over the exam so you can practice, okay? Because it looked like a lot of students were struggling for chapter 16 and chapter 17. So for these exam corrections, feel free to use the study guide and lecture notes, okay? And then once you finish the exam correction, you need to scan it in a PDF file and then upload it on Web Campus to the same location that you submitted the extra credit submission. Okay, it's going to be under the assignment tab, location name extra credit submission. Okay, so attach another file, okay, and put a title exam correction. Okay, I will post a detail. If you send me an email, I will send you the detailed information through the email. Okay, again, I'm not going to receive any email submission. Okay, you should send me an email so I can communicate with you. I can hand you over the exam, but in order to submit the exam correction, you need to submit through Web Campus. Okay, so if you really want to improve your exam score, send me an email. And then another thing is, for the extra credit, I was looking over a lot of students' study guides, and I realized that most students, their study guide was very, very short and brief. Some students, they just wrote few equations and they call it study guide. That's not a study guide. I specifically ask students to paraphrase everything in their own words. So oh, so this was my study guide. Okay. You guys should paraphrase everything in your own words and then add more stuff to my study guide. You guys should be studying more than how I prepare for this exam. Okay, so it's not acceptable that your study guide is very, very, very brief and short and just consists of few equations. Okay, so for those study guides, I gave them 0 for the extra credit. Okay, I'm not going to accept those study guides. This study guide is very, very important because this is what you're going to be using for to prep for the final exam. During the final exam, you're not going to have enough time to go back to chapter 16, chapter 17, or previous chapters and prepare a study guide. By the time when you are preparing for the final exam, you're going to forget a lot of the previous chapter materials. So that's why when everything is fresh in your mind, preparing a good, thorough, detailed version of study guide is important. Okay, so even if you don't need to prepare a study guide for the extra credit, I highly suggest and recommend you guys preparing your own version of study guide, a very, very thorough and detailed version of study guide. Your study guide has to be longer and more detailed than mine, okay? But I see that only a few students prepare a pretty good version of study guide. Most students, they were just copying and pasting whatever I wrote on my study guide, or some students just submitted a highlighted version. They highlighted on my study guide and they submit it. Okay, then I'm not going to give out extra credit for those who did not put effort for study guide, because that's not fair for those who spend hours and hours preparing a good version of study guide. Okay, so the due date for the extra credit is going to be this Sunday. You have plenty of time if you want to, if you receive 0 score for the extra credit, if you want to resubmit your study guide, please go ahead and do that. Okay. If you don't want to get extra credit, that's totally fine too. Okay. Again, exam correction is also an option. Okay. It's not required. It's not obligated. It's only for those who really, really need to improve their exam score for exam 2. Okay. So if you're interested, send me an email.
Professor,
Mm-hmm.
I just wanted to say thank you.
Mm-hmm.
But also, When is the exam correction due?
Oh, good question. Exam correction is also going to be due this Sunday. Okay, so yep, it's going to be due this Sunday, and then for chapter 17 is chapter 17 homework supposed to be due this Sunday?
Yes.
No, chapter 16 homework was supposed to be due this Sunday, right?
I think it was chapter 17.
No, it's chapter 16.
17 is due this Sunday.
Chapter 17 is due Sunday, and chapter 16 was due like 2 weeks ago, I think.
I think I gave an extension for chapter 16 homework.
I just checked, and the extension was given for chapter 17, so it is due this Sunday.
Okay. Okay. In that case, because you know, some people they want to do the extra credit again, and they want to do the exam correction. So a lot of things going on this week, right? So I'm going to extend the deadline for chapter 17 homework. Okay. So I'm going to chapter 17 homework is going to be due April 3rd. How about that?
Thank you, Dr. Lee, so much, Doctor.
Yeah. So
Thank you, Dr.
chapter
Lee.
so yep, let me change it right now. Oops. Okay. So the due date for chapter 17 homework is going to be postponed to April 3rd. Okay. So April 3rd. Okay. So about the exam corrections, if you're willing to do the exam correction, feel free to discuss with your friends, create a group to study, do whatever you want to do, but do not bring the exam correction to the tutoring center or SI instructor to ask for help. Okay, try your best to utilize all the resources that you have, your book, your note, your study guide, my study guide. Those should be more than enough for you to complete the exam. The exam correction. Okay. Another announcement about the exam is that I made a mistake. So for question 10, question 10 was about a question where you have aqueous basic solution. Okay. Okay, you have aqueous basic solution. The concentration of this anion was given. Okay, and then the Kb value was given. It was asking for hydroxide concentration. Okay, so I promise you guys, and I've already told you guys that for these type of question, you are you don't have to you can just assume that the x is very small and you don't have to solve for quadratic equation. Okay, but so the answer should have been D, but then I mistakenly put it as B because I accidentally solved the quadratic equation for this question. Okay, so for this question, anyone who chose B, anyone who solved the quadratic equation will also get the full points. Anyone who chose D, who did not solve the quadratic equation, will also get the points. Okay, so for those who chose B and D for question 10, they will receive full points. So when you do exam correction, if you got anything other than B or D, you have to do exam correction for question 10. If you got anything either B or D, you don't have to do exam correction for question 10. Okay. Any question?
On the exam, is it going to be marked which one is right and wrong?
On the exam, which one is marked right or wrong? What do you mean?
They're going to show us which ones we need to correct.
So if you log on to Web Campus, you should be able to see which question you got incorrect.
Okay, thanks.
All right, let's continue. And then, oh yeah, go ahead.
For the extra credit, if we got the points, will those points be added to our exam grade?
Correct.
Okay.
Yeah. Correct. All right, and then you guys will be doing the exam correction, and if there are still a group of students who desperately need help for chapter 16 and chapter 17, this is very, very important chapter, and again, it will appear on final exam. Okay, a lot of big portion of it will appear on final exam, and you don't want to you know you want to do well for the final exam. So if you're still struggling chapter 16 and 17 after doing the exam corrections, what I'm planning to do is maybe next Friday, okay, when I think Friday is good because most students don't have class on Friday. I will be on campus, second floor chemistry building, the learning center, okay, so that you guys can come over. We can go over or solve the exam questions and some of the sample exercises together, and to really clear up the portions that you guys are struggling. Okay, so that's what I'm planning to do. But for now, if you wish to do exam correction, focus on that. Exam correction and extra credit are both due this Sunday. Okay,
Professor,
go ahead.
what time would you be on campus next week on Friday?
Friday, let me see. Probably sometime 11 to 1, or I haven't decided yet. So what time would be good?
Okay, thank you.
Yeah, I'm asking what time would be good for you guys. Just, let me know.
Okay.
Does anybody have class on Friday, like labs or anything?
I have a lab, but it starts at 1, so anywhere in the morning would be good for me.
Okay, so if you're gonna come, then I can do it in the morning. So yeah, maybe sometime in the morning, maybe 10 to 12 or something like that. Okay,
Yeah, the
so
morning would work better. Thank you.
morning would be better. Okay, yeah, so that's next Friday, but let's not focus on that for now. For now, just focus on exam 2. Okay, again, if you're satisfied with your exam 2 grade, that's totally fine with me. Okay, uh, grading exam correction for you guys is a lot extra work for me, so um, uh, um, it's not like I want you guys to do the exam corrections, but if you really need to boost your exam 2 grade, um, then I'm giving you an option. Okay. All right. Let's move on to the solubility and solubility product. Okay. So solubility and solubility product constant. Solubility in KSP are different. The solubility is ability of a substance to dissolve. Okay. Solubility is known to be the maximum amount of solute that can be dissolved in a solvent at equilibrium. Okay. Solubility is a quantity of a substance that dissolves to form a saturated solution. Okay. It has a unit of gram per liter or mole per liter. Okay, so these are the common units for solubility. But KSP is not, it's not solubility. This is solubility product constant. This is the equilibrium between solid and its respective ions in a solution. Okay, the value of the constant identifies the degree of which the ionic compound can dissociate in water. Okay, the degree. This is the solubility, is the amount. Okay, so this is a degree of which ionic compound can dissociate in water. So KSP is unitless, while solution has unit of gram per liter or mole per liter. Okay, again, high KSP value means the higher the KSP, the more soluble the compound is in the water. The lower KSP, the less, the more insoluble the compound is. So uh, the lower the KSP, the less soluble the compound is in the water. So again, since solubility and KSP are different, if we are given solubility information, these are the solubility information, right? If we're given solubility information, we can follow this green arrow to find KSP value. Or if we're given a KSP information, we can follow this red arrow to find the solubility of a compound. Let's try a sample exercise. The KSP for calcium fluoride is this, okay? You can find this value back of the book. Assuming equilibrium is established between solid and dissolved calcium fluoride, and there are no other important equilibria affecting the solubility, calculate the solubility of calcium fluoride in grams per liter. So in this question, we are given the KSP value and are asked to you guys can stop sending me emails. You guys can send me emails after this class. So as of right now, let's focus on this lecture first, okay? So in this question, we are given a KSP value, okay, and are asked to find the solubility of this compound in gram per liter. Gram per liter. Okay, so again, KSP is the equilibrium constant, solubility product constant. Solubility is the quantity or amount that can dissolve in solvent. They're different. Okay, so in order to find the solubility using KSP information, we need to follow the red arrow, right? Let's find the molar concentration first. Just how we dealt with Kc in previous chapters, in order to find KSP, we need to use concentrations of ions at equilibrium. Okay. Need to use concentrations at equilibrium. Okay, so let's create a table to find the initial concentration, change in concentration, and most importantly, in equilibrium concentration. Okay, so the equilibrium reaction for a calcium fluoride dissolving in aqueous solution looks like this. The initial concentration, I mean, the solid is not going to be included in the KSP expression, so we don't have to write any, we're going to ignore it, okay? As for the calcium ion and fluoride ion, the initial concentrations of these will be 0, right? You don't have anything to start off. The change in concentration will have positive sign because you're generating these ions, right? And according to stoichiometry, you have 1 mole of calcium ion, 1 mole of calcium ion, and 2 mole of fluoride ion generated. So the change in concentration is going to be positive X for calcium and positive 2X for the fluoride, right? So then the equilibrium concentration is going to be X and 2X. The KSP expression is therefore calcium concentration times fluoride concentration raised to power of 2, right? Because you have coefficient of 2. But let's plug in this equilibrium concentration. We have X times 2X squared, which is 4X cubed. Okay, if you solve for X, then the KSP value is already known, right? So we know that KSP is 3.9 times 10 to the negative 11. Okay, if you solve for X, you take 3.9 times 10 to the negative 11 divided by 4 and raised to the power of 1/3, you get 2.1 times 10 to the negative 4. So the X is 2.1 times negative 4 molar. So this is the equilibrium concentration of calcium ion. The amount of dissociated calcium ion is whatever the amount calcium fluoride that was able to dissolve in water, right? So if you generated this amount of calcium ion, if this amount of calcium ion dissociated, this tells us that this amount of calcium fluoride were soluble in water. Okay, you should be able to make the connection. So, because 2.1 times 10 to the negative 4 molar calcium ion dissociated, this tells us that 2.1 times 10 to the negative 4 molar of calcium fluoride was able to dissolve in water. Okay, I hope this makes sense to you guys. So therefore, the solubility of calcium fluoride is is 2.1 times 10 to the negative 4 molar or mole per liter. This is same as this, right? But since the question wants the answer in grams, since the question wants answer in grams per liter, we need to convert this mole per liter to gram per liter. We can leave the L in the liter in the denominator as it is. We just have to convert mole to gram. So in order to do this conversion, we need the molecular weight information from the periodic table. The molecular weight of calcium fluoride from the periodic table is 78.1 gram per mole. Okay, so in order to convert this to gram per mole, you take 2.1 times 10 to the negative 4 mole per liter times 78 times 78.1 gram per mole. You will have mole and mole cancel each other and you are going to be left with gram per liter. So that equals to 1.6 times 10 to the negative 2 gram per liter. Okay, So this is the solubility of calcium fluoride in gram per liter. Okay, so we did follow this map. We first found the molar concentration of ions at equilibrium, and then we used that to find the molar solubility of the compound in molar solubility, so mole per liter, and then we found the solubility in gram per liter. Okay. Let me know if anyone need more time for
Dr.
this.
Lee,
You wanted me to go back?
why didn't we take the concentration of fluoride ion?
For this,
Yes.
you can use this. That's totally fine. But then you need to divide it by 2 because 1 calcium fluoride dissociate into 2 mole of fluoride, right? So in that case, you have to divide it by 2. So that's basically the same thing. I just use this because 1 molar of this salt dissociate into 1 mole of this. Does that make sense?
Yeah, it does. Thank you.
Mhm.
You get the molecular weight of which ion?
So you want to convert mole per liter of this compound into gram per liter, right? So then what molecular weight information do you need? You need molecular weight information of this, right? Does that make sense? Got it? Okay. All right, factors affecting solubility. Solubility is affected by various factors, and in next few slides we will learn about these factors that have major influence on the solubility of a substance. Okay, so the first factor that affects the solubility of a substance is a common ion effect. This is the first factor that affects the solubility of a substance. So if one of the ions in a solution equilibrium is already previously dissolved in the solution or being added to the solution, then the solubility of the salt will decrease. For example, let's say you are trying to dissolve this salt. If you already have calcium or fluoride ion floating around the system, or if you are continuously adding this or this into the system, what's going to happen to the equilibrium? According to the Le Chatelier's principle, if you're adding something, the equilibrium will shift to consume that whatever's added, right? So if you keep adding this, the equilibrium will shift to left. Okay, so then what's going to happen? The solubility of this salt will decrease because the equilibrium is now shift to left. Okay, so in that case, if you keep adding this common ion, less of this salt will be soluble in water. Another example. Oh, not this is the how you add the common ion. You see this graph? Sodium fluoride and calcium fluoride. What are the common ion between these two salts? Fluoride. This is the common ion. So if you keep adding sodium fluoride into the solution, so you have a bottle, you have water, you have calcium fluoride. You're trying to dissolve this. Into this bottle, what if you keep adding sodium fluoride? What are you adding? Sodium fluoride is a soluble salt. Okay, so the more sodium fluoride you add, the more fluoride you're adding into the system. So then if you're adding more of this fluoride, what's going to happen to the equilibrium? Equilibrium is going to shift to left. So then the solubility of calcium fluoride is going to decrease. So as you can see here, due to the addition of a common ion fluoride from sodium fluoride, the equilibrium, as you can see that the solubility of calcium fluoride drops as more and more fluoride is added to the system. Let's try a sample exercise. Calculate the molar solubility of calcium fluoride at 25 degrees Celsius in a solution that is 0.01 molar in calcium nitrate and 0.01 molar in sodium fluoride. So in this question, the insoluble or let me bring this solubility table down. Okay. Okay. So according to this table, is it clear for you guys now? Or is it still blurry?
It's clear.
It's clear? Okay. All right. So in this question, you have calcium fluoride, salt, and you are adding calcium nitrate. Okay. Is calcium fluoride soluble salt or insoluble salt? Calcium fluoride is going to be, the fluoride is not included here. Okay. And then the solubility table, if you are solving, if this type of question appear on final exam, or it's going to appear on exam 3, right? So the solubility table will be given to you, and then it will specifically indicate that whether the salt is, if it's not included in the solubility table, I will indicate whether the salt is going to be insoluble or soluble. Okay, so calcium fluoride is insoluble salt. Calcium nitrate, anything with nitrate is going to be soluble. Okay, so we know that this is a soluble salt. Oh, give me 1 second. Okay. So I'm not sure if you guys can recall from Gen Chem 1, but all the ionic compounds that contain in group 1A, ionic compound containing group 1A elements in periodic table, they're all going to be soluble. So if you go to periodic table, group 1A elements are going to be lithium, sodium, potassium, rubidium, cesium. Okay, so any ionic compound contains these metals are going to be soluble. Okay, you don't even have to go to this table. Okay, so anything with sodium, you know for sure they're going to be soluble salt. Okay, so we know for sure this is going to be soluble. Okay, and other ionic compounds refer to this table, or for example, calcium fluoride. The fluoride is not included in this table. In that case, I will specifically indicate that whether it's going to be soluble or insoluble. Okay, so we know that calcium fluoride is insoluble, okay, or slightly soluble to be more incorrectly saying. Okay, it's slightly soluble. Okay, calcium nitrate is fully soluble. It will dissociate 100% in aqueous solution. So let's focus on
Professor?
yeah.
So for the ionic compound containing group 1A,
Mhm.
does it have to have more than one ion to be considered soluble, or if there's just one ion of group A, then it's soluble?
So here, yeah, the group 1A metal, right? So they're going to be, if your cation is cation is from group 1A, you know that that ionic compound is soluble. Does that make sense?
Yeah, it does. Thank you.
Okay, so now let's create a table to find the equilibrium concentrations of ions after addition of calcium nitrate. Okay, so you have an aqueous solution that has calcium fluoride, but you are adding calcium nitrate into the system. So because this is a soluble salt, as soon as you add into aqueous solution, it's going to dissociate, right? If it dissociates, these will be floating around the system, right? So then if we were to find the initial concentration, change in concentration, equilibrium concentration, initial concentration of solid, we're not gonna disregard for now. For this calcium, previously when we don't add anything, we know for sure that this is 0 to start, right? But right now you are adding calcium nitrate to start off, so you have additional calcium ion floating around the system. So this means your system previously already has calcium ion dissolved. So therefore, initial concentration of calcium ion is going to be whatever concentration of calcium nitrate that was dissolved initially, which is 0.01 molar. Are you adding any fluoride into the system? No, right? So initially you don't have any fluoride in the system, so the starting initial concentration of fluoride is going to be 0. As for the change, the concentration will have positive signs, okay, for both ions because you're generating these ions. According to the stoichiometry, you have 1 mole of calcium and 2 moles of fluoride generating, so then the change in concentration is going to be positive X and positive 2X. If you apply this change, the equilibrium concentration for 2 ions is going to be 0.010 molar time plus X, and then for fluoride you have 2X. The KSP expression, okay, again, KSP, you need to use equilibrium concentration, right? So the KSP is going to be calcium concentration, fluoride concentration raised to the power of 2 equals 0.10 0.010 plus x times 2x squared. We know that the KSP value is given, right? Back of the table or previous slides, it was given as 3.9 times 10 to the negative 11. Okay. So again, since we know that only tiny amount of calcium is going to will dissociate, okay, because calcium fluoride is considerably insoluble salt, right? So we will assume that X is very small. So we will ignore adding tiny value of X into when we find the equilibrium concentration for the calcium. However, multiplying a small number could generate totally different results. So you should keep X in finding the equilibrium concentration of fluoride ion. Okay, when you're adding a very tiny number, you can ignore. Okay, so then the KSP expression is going to be 0.010 times 2x squared equals 3.9 times 10 to the negative 11. So if you solve for x, you're going to have 3.1 times 10 to the negative 5 molar. So the amount of calcium ion dissociated from the dissociated is from the amount of calcium fluoride dissolved, right? The amount of calcium ion at equilibrium is 0.010 plus x mole. However, this amount is coming from another salt. Okay, so how much calcium ion is from calcium fluoride salt? Just this salt. It's going to be the x mole. So the molar solubility of calcium fluoride is basically X. Does this make sense to you guys?
Yes.
Molar solubility of calcium fluoride is also 3.1 times 10 to the negative 5 molar. Okay, because whatever this amount dissociates will give you whatever amount this salt dissolves in water will give you calcium ion that has been dissociated. Okay, so this is a molar solubility, and then same thing for B. Okay, I wish I have time to do B, but we're running out of time, so I'm going to skip B. You can do the solve the problem B by itself. Everything's just going to be exactly the same. Okay, but in order to properly solve these type of questions, you need to recognize the common ion first. Okay, so for question A, the common ion between calcium fluoride and calcium nitrate was calcium, right? Now think what's the common ion between calcium fluoride and sodium fluoride? It's not calcium, it's fluoride, right? So yeah, same. You should take the same approach, and you should easily solve question B as well. All right. The second factor that affects the solubility of a substance is pH of the system. Okay. The first factor is common ions. The second factor is pH of the systems. Let's say you're trying to dissolve insoluble or slightly soluble salt magnesium hydroxide. Okay. When this is insoluble or slightly soluble salt, when small amount of this salt dissociate, you get magnesium plus hydroxide. What happens if you have another acids in this solution? Wouldn't this acid react with hydroxide? So if whatever hydroxide that is being generated in the system is keep getting consumed by this acid, you are continuously decreasing the hydroxide concentration because acid is consuming the hydroxide. So where does the equilibrium shift in this case? Because you are depleting this, you're consuming this, the equilibrium will now shift to right. Again, Le Chatelier principle, right? If you're depleting something, the equilibrium will shift so that you make more of what is being disappearing, right? So if the equilibrium is shift to right. So therefore, due to the equilibrium shifting to the right side, more of the magnesium hydroxide salt will dissolve in water. Okay. In general, the solubility of a compound containing basic anion, this compound contains basic anion, right? Or anion of weak acid, okay? Basic anion or anion of weak acid. This will increase the solution, this, the solubility of a compound containing basic anion increases as the solution becomes more acidic. Okay, so in acidic solution, the solubility of this salt is going to increase. Why? Because hydroxide that's being dissociated is keep getting consumed by acid. Because you are decreasing the concentration of hydroxide, the equilibrium shift to the right. Here's another example where pH affecting the salt solubility. Let's say you're dissolving lead fluoride in water. This is an insoluble or slightly soluble salt. If the small amount dissociates, you will have lead plus 2 fluoride. What happens if you add acid into the system? What happens if you add acid into the system? Wouldn't the added hydrogen react with fluoride? Fluoride is anion of weak acid, right? Hydrogen fluoride. Fluoride is an anion of weak acid. So this anion of weak acid has basic property. It loves to react with any proton of the acid within the system. So in this case, the fluoride ion that is being dissociated will keep interacting with hydrogen. It will get consumed by hydrogen within the system to produce hydrofluoric acid. This is a side reaction, right? To produce hydrofluoric acid. Okay, so if fluoride keeps getting disappearing, where would the equilibrium shift to? The equilibrium will shift to the right to produce what's being disappearing. Fluoride is keep being disappearing, right? So therefore, lead fluoride solubility will increase as you add more acid into the system. Okay, so that's what this figure is showing. However, let's say you have, for this example, you have let's say for this example, you have lead iodide. If you have lead iodide, very small of that lead iodide dissolve and create these ions, for example. Since iodide is anion of strong acid, what do you guys recall from the acid chapter that what characteristic of anion of strong acid has? Anion of strong acid, such as iodide, is pore base. This anion will be reluctant to react with any acid that is being added into the system. Okay, so even if you add acid, proton, this will not react with this anion. Therefore, addition of acid into this system will not have any effect in the solubility of the lead iodide in the aqueous solution. Okay. So adding acid into this increase this salt's solubility. Adding acid into this system, it has nothing to do with, it's not going to affect solubility of this ionic compound. Okay, so let's try a sample exercise. Which of these substances are more soluble in acidic solution than in basic solution? So which of these insoluble or slightly soluble salts are going to be affected by having acid in the system? Nickel hydroxide, when dissociated, will generate nickel and hydroxide ions. Hydroxide will react with water, okay, to generate water, right? So because added acid will interact with this anion, you know that this will be more soluble when you add acid. For B, calcium carbonate. Your anion is carbonate. For calcium carbonate, the carbonate is an anion of weak acid. Okay. What property does anion of weak acid has? It has basic property. It will react with any acid that's being added into the system. So then what happens? The salt is going to be more soluble when you add acid. C, barium fluoride. Fluoride is also an ion of weak acid. Okay. Copy. Okay. Because if fluoride is anion of weak acid, this will react to, it has basic property, and this will react with any acid proton in the system. So this salt is going to be more soluble when you add acid. D, silver chloride. Silver chloride is an ion of strong acid. Hydrochloric acid is strong acid, right? So then, because anion of strong acid has very, very poor basic property, it has no capability to steal the proton, okay? Or it has very low capability of reacting with proton in the system. So any acid in the system, chlorine is not going to do anything with them, okay? So the salt solubility is unaffected by the acid in the system. Solubility of salt is unaffected by acid in the system. Okay. The third factor that affects the solubility, the factors that affect solubility that we have observed so far is common ion, pH. The third factor is formation of complex ion. Okay, so the characteristic property of metal ions is that they can act as Lewis acid and form complex ions with Lewis base in the solvent. For example, let's say you have insoluble salt silver chloride. Okay, tiny amount of this salt or slightly soluble salt that dissolve in water will dissociate into silver and chloride ions. And let's say you're adding aqueous ammonia solution into the system. Okay, so you have a solution with silver chloride, and you're adding aqueous aqueous ammonia solution into the system. What's going to happen is that ammonia act as Lewis base side reaction. What's going to happen is ammonia will act as a Lewis base, silver metal act as Lewis acid, they will react. Lewis base, Lewis acid, they will react. And then form silver then what happens due to this reaction, which ion is going to be disappearing? Silver, right? The added ammonia in the system is continuously consuming this silver. So then, because silver is keeping disappearing, the equilibrium will shift to which direction? It will shift to right? So then what's going to happen to this salt? Silver chloride will be more soluble because the equilibrium is now shifted to the right. Silver chloride will increase in solubility. Equilibrium shift to right. Why? Because silver ion is keep getting disappearing. Why is it disappearing? Because ammonia is reacting with this. So the resulting ions from reaction between metal ion act as a Lewis acid and Lewis base. This resulting ion is called complex ions. Okay, so this is called complex ions. Here are some of the metal complex ions that can be formed. So this should be all. I don't know why it's appearing as a square. Okay, so these are the some of the metal complex ions that can be formed. Okay, as you can see, metal ions, all these metal ions act as Lewis acid and reacting with Lewis base. Okay, the resulting ion is called, these are all called complex ions. Okay, and I know what question you guys are going to ask. Do we have to memorize this table? The answer is no. Okay, so you don't have to memorize anything from this table. These complex ions are ions, so they are soluble in water. Because they're soluble in water, they will have equilibrium constant as well. It is denoted as Kf. Okay, so this equation, you can write equilibrium expression for these common ion. It's denoted as Kf. So please don't get confused between, we've learned a lot of equilibrium constants, right? We've learned Kc, Kp, Kw, Ksp today, Kf. You should be able to distinguish all of these equilibrium constants for the final exam. Okay?
Professor,
Uh-huh.
before we leave, I have a question about slide 44.
Yeah,
So,
my screen is frozen.
oh, it's okay. It just, you were talking about how more acidity equals more solubility or something like that, but I'm not sure if I heard you right.
More acid, more solubility.
Yeah.
Here?
Slide 44.
Slide 44. Is this slide 44?
It says 46 on your screen.
44, is it this?
Yeah, that one.
Okay. What's your question?
You mentioned something about acidity, but I'm not sure if it meant if more acidity equals more solubility, because I'm not sure if I heard you right.
More acidity, more solubility. So more, what does it mean by more acidity? If you're adding more acid into the system? Is that what you mean?
Yeah, that's something,
Yeah.
I'm not sure what you said around there because I got lost, but
Oh, okay.
yeah,
All right. So if you add more acid into this system, acid is HA, right? Any common acid we label as HA. Do you agree?
correct.
Yeah. So if you add acid into this system, what's acid gonna do? Acid will eat up this hydroxide that is being formed, right? Do
Yes,
you agree with that? Yeah. So what happens if your hydroxide concentration keeps getting decreased? If hydroxide keeps getting disappearing because it's reacting, it's consumed by this acid, what's going to happen to the equilibrium? Because this concentration is decreasing, the equilibrium will shift to right? According to the Le Chatelier's principle.
yes,
So if the equilibrium shift to right, that means more and more of these salts will try to dissolve to create more hydroxide within the system. Does that make sense?
it does.
Yeah, so eventually the conclusion from this whole phenomenon is that if you add more acid, more salt, this insoluble salt, more of this insoluble or slightly soluble salt is going to um, be more soluble, have higher solubility. Does that make sense?
It does. Thank you so much.
Uh-huh. All right, that's the end of today's lecture. Um, I gotta go, but does anybody have urgent, immediate question? Okay, I wrote this and it's gone. KC, KP, KW. Why is it lagging? KSP, KF. Be able to distinguish all of these. They are all different, okay? They are all equilibrium constants, but equilibrium constants for used for different occasions, okay? So be able to distinguish all of these. All right, so if nobody has any other questions, I'm going to end the meeting here, okay?